For our second talk, we have Mishmash, also known as Mike. He recently moved all the way from Bristol. He moved to Chiswick, is that right? He actually moved in yesterday. And he still found time to do a talk. This is like above and beyond. It's incredible. Going to talk about optimization today, aren't you?
Yep.
Yeah, really looking forward to this. I need some tips. Please take it away.
So I apologize if this talk's a bit technical and not as interesting as Victor's, but I'll try and keep it relevant. Just to start, I'm going to give you a quick overview of what I'm going to be talking about. And this is quite a sort of computer sciencey approach to optimization, but I think it's quite relevant in sort of laying a foundation for kind of how you could approach development in the future if you don't already know about these things. The second is gaining an understanding for how GameMaker as an engine works. And this is kind of understanding things like how things actually are running on the CPU, understanding how GameMaker processes things, where the slowdowns are, things like that, understanding the graphics pipeline a little bit. Third is actual practical optimization techniques. So these are kind of, again, I'm trying to keep it high level, so not much code as such, but sort of approaches that you can take forward into your own projects to try and speed things up. And it's more about the thought process that goes into it and what order you should kind of consider things in, rather than just straight like code things. And finally, just talk on when optimization becomes relevant, why it's relevant for some projects. And generally speaking, it is for most people, even if you don't think it is. So yeah, the aim is as I've just described. So the first thing, just really going to skim over this because it's not that important, but it's an idea of algorithmic complexity. And in computer science, we've got a notation, which is referred to as big O notation. And this is kind of a way of quantifying the performance of different algorithms. And the very first thing you want to consider when looking at optimizations and trying to work out why something might be slow, why it's not performing as well, is to kind of consider the algorithmic complexity. And what this describes is how algorithms scale as your game gets bigger. So for example, something ON is called linear scaling. And what this means is for everything that you're running the code for, it scales linearly. So if you've got 100 enemies and they're all running their step event, it's going to be like it's going to take 100 lots of that step event running. If you've got 1,000 enemies, 1,000 times, it's linear. The more enemies you have, it gets progressively slower, but each enemy takes kind of a fixed amount of time. So here's an example of some code. If you're iterating over a list, the amount of time this code will take to run is dependent on the size of the list. And as you add more elements to this list, this summation starts to take longer. Yeah, so this is all quite simple stuff. You can read more into this. There's a whole theory behind it, but it's kind of slightly relevant. So here we've got n squared is similar, but the idea here is that the scaling becomes much worse. So for each element you add, you square the time it takes, basically. So 2 elements takes 4 iterations, 3 elements takes 9, 10 elements takes 100. And that means you have this kind of exponential scaling where things get slower and slower and slower to the point where your game's crawling. So this is an example of a list, but you could apply this to all sorts of things like collision systems. If you've got 100 enemies all performing collisions on each other, it's not linear because every enemy is having to check against every other enemy. And things like that really inhibit your ability to scale your games because you can no longer just keep on adding as many enemies as you want. You've got to start applying limits where you maybe don't want to. And so that's kind of why I'm running over this quickly. The next thing where this is relevant is it's quite common that you use data structures in your game. And each data structure has got its own performance cost. So grids are the fastest data structure in GameMaker. They're faster than arrays. And this means that you can change elements basically instantly. There's not much performance cost doing operations on a grid. So for anything that's fixed where you need like a nice large block of data, using grids is really good. The next lists, they're actually quite bad. They're convenient to work with, but when you start doing things like deleting, inserting, or searching through a list to find a value, those operations can get really slow. And if you're relying on those data structures for aspects of your game, they can slowly chip away at the overall performance. And depending on the exact use case, you could consider using a different data structure. Maps are quite quick as well, and they're actually really memory efficient as well. So the problem with a grid or an array, if you've got if you need to be able to key on 1 million different elements, that's going to take up a huge amount of memory. But you might not even be using all those. So for example, instance IDs start counting 100,000. And if you wanted to use an instance ID to say look up some value in a list that corresponds to that instance ID, you're going to need a massive array to be able to account for those instances. And given that some of them might not exist anymore, you're better off using a map which will only use as much memory as there are entries in the map. So this is just a quick overview. If it's not that relevant to you at the moment, it doesn't really matter. But yeah, so the next thing is profiling. And the job of profiling is to basically work out what things in our project are slow or not working as they should be, whether it's identifying performance leaks or anything like that. The first step is kind of to try and build an intuition for what you think might be running slowly. It's like, oh, well, I noticed when playing the game that I walk into this new area and it suddenly gets really slow. And so you might start constructing some ideas like, oh, there's too many new objects appearing in this area. There's a really heavy particle effect. And you kind of build an intuition about what that might be. And then you actually use the profiler, which is built into the debugger in GameMaker, to actually quantify your assumption. So for example, you can find the scenario where you think there's a slowdown and turn the profiler on, walk into that room, and it'll give you a performance breakdown like this, which shows you basically how much time each aspect of your project is taking. So for example, here in my game, the control step takes up 21% of overall runtime. From that, we could extrapolate, oh, wait, maybe this is doing too much. And so for your game, you might find that, oh, suddenly the particles are taking up an enormous amount of performance when they shouldn't be. Like, you don't want to be one fire effect taking up 70% of your runtime, for example. The final thing is a little trick that a lot of people don't know about is that the FPS real value actually is just 1,000. Well, if you do 1,000 divided by FPS real, it gives you the amount of time it took to process that entire frame. This information is really relevant if you're trying to target a particular frame rate. So for example, if you're trying to get your game to run at 60 FPS, that gives you 16.6 milliseconds as your total frame budget. And if you do this calculation, which is 1,000 divided by FPS real, this will give you, in this example, where the FPS real is 400, that'll give you 2.5, meaning that you're only using 15% of all your performance. And that gives you a quantifiable way to say, okay, I can add this much more and have this much more going on before things start becoming a problem. It also gives you enough wiggle room. So if you're trying to target a particular type of hardware, you can run your game on that type of hardware and sort of work out why it's, well, how much performance you're using, how much you've got left. If you want to target like a low-end laptop, for example, and you run your game and you're almost using your entire frame budget, then you probably need to consider performing some form of optimization before you can begin adding new visual effects or new features to that game. The next thing I want to talk about is just a quick overview of GameMaker as an engine. So most of you probably know that the default GameMaker runs as a virtual machine. A virtual machine basically just emulates a CPU. So GameMaker code compiles down to a series of instructions. These instructions will run on the CPU through the virtual machine. The important thing to note here is that a lot of the stuff in GameMaker actually runs inside a native C++ runtime. So things that aren't your code, but functions that you call, so for example, instance creation, collisions, and the graphics pipeline are all managed natively. And that means that they're actually quite fast already, and it's kind of difficult to gain performance on them. You may know that GameMaker also has an option called YYC, which allows you to compile your games down to native C++ code. And the important thing to note here is that YYC doesn't only speeds up the code that you write, but not what GameMaker as an engine does. And this is quite a common misconception. There will often be like some side effects, so your game will likely get a slight bit of increased graphical performance or performance from other areas just from being entirely C++. But only your code will run faster, generally speaking. So that's all the logic that you write for enemies, for the player, but not the functions that GameMaker calls upon itself. And yeah, YYC is obviously a really good way to make your game run faster because you're running native code rather than through a virtual machine. The next thing I want to kind of discuss is the graphics pipeline. A lot of people, again, they kind of always they look at engines like Unity and then they see GameMaker and it's like, oh, GameMaker, like Unity can render these massive 3D scenes and GameMaker can only do like 5 things at once. And a lot of people make the assumption that, oh, this must be because GameMaker's graphics pipeline is slow. And I want to create kind of a distinction here, and it's often that the GameMaker's graphics pipeline is actually quite optimal for what it does. And it tries to optimize things as best it can, but generally how people use GameMaker affects how fast it runs. And because GameMaker gives you so much freedom and so much control over your rendering, you can end up indirectly, accidentally making your game slower without even realizing it. So some of the optimizations that GameMaker does is texture management. You might see that in texture pages. The reason that sprites are grouped into texture pages is because on the GPU, it means that we can render lots of different things without having to swap texture memory around. Every time that you change texture to a different texture page, inside your GPU, you've got to flip which texture is currently being used, and that incurs a performance penalty. On good graphics cards, it's smaller. You could probably perform hundreds of texture swaps per second. On a bad graphics card, especially on laptops, that can really start to bite. And just by better management of texture pages, you can really speed up your performance. So that's things like putting graphics that are from the same scene into one texture page, putting enemies that are going to be on the screen at the same time, or have their animations the same into the same texture page, and so on. Another really important thing is draw call batching. So every time you call to draw something, that needs to send a little message to the GPU to tell it to draw it. And the communication of these messages is really slow. So the graphics API's responsibility is to transfer data and manage the communication between the CPU and the GPU. So every single interaction, every draw, every time you want to change texture, every time you want to change some rendering property, whether it's the color, the blend mode, things like that, a little message is sent from the GPU or from the CPU to the GPU, and this is where most games slow down. So most games are like most games in GameMaker are rarely using their full CPU usage, and they're rarely using the full GPU, but they run slowly nonetheless. And that's because the bridge in communication between the two is slow. And well, it's fast, but it's not as fast as the CPU or the GPU in their own right. And so it's this communication bottleneck which is causing most problems. And so if you understand the sort of things that can optimize the transfer of data, again, the faster you can build your games. And so draw call batching, for example, means that if you do 10 draw calls back to back, which don't require any texture changes or any color changes or any blend mode changes, all of those get grouped together into one message. And just that sending of one message is infinitely faster than sending 10 individual messages. So you can kind of think of it like networking, where you've got two different computers, and even though both computers are running quickly, you still have latency in online games, which affects the user experience and affects the actual ability for the games to run faster, because you're just waiting on data to move around. The next thing I want to comment on, just a quick oversight, is again, a lot of people kind of say, oh, well, shouldn't GameMaker use Vulkan or some really good API that will make our games run really, really fast? And no, there's kind of a misconception that will just automatically make your games faster. And they kind of harp on your games saying, oh, can you please like upgrade the API? But actually, in order to get the most out of the APIs, it requires you changing the entire way the graphics pipeline works. Both of those APIs are written to basically reduce that communication bottleneck that I talked about earlier. And so just plugging it in would make virtually no difference to any game. You'd actually need to change the way the game was written. And a lot of the things that you do to improve games are things that you can do independent of the API. So again, this is kind of what I've talked about before. And so with these APIs, yeah, you can speed up the projects and by just understanding this data transfer, basically. And you don't necessarily need a more modern API to get more out of your games already. You can just employ some of those strategies to try and speed up what you've got. So this is a code example of what I've described. These are two samples where we're both trying to draw a scene. And both of these should produce virtually the same result. We've got three different types of object: enemy A, enemy B, and enemy C. And we're just basically looping through the objects and just drawing them. But this example is likely to be far faster than this one because we have explicit control over how things are being rendered. In this one, the order in which the enemies are rendered will be based on their creation order by default. And so if you've kind of got interspersed creation of object A, object B, and object C, and the rendering processes for those objects incur some sort of state change between them, then you could potentially just be losing a lot of performance. So by restructuring your rendering and having a more explicit control and sort of grouping together things that share a common rendering technique, you can actually speed up your games quite a bit. Now, sort of getting on to stuff that's a bit more relevant. These are some sort of ideas that you can have that might help you change the way that you approach development. So a lot of things, it's really easy to over-engineer things. Like you come up with an idea for something you want to do, and you're like, oh, we need this crazy pathfinding algorithm that does this, that, and that, and that. And it ends up being horrendously complicated, and as a result, probably not very performant either. So that's kind of the first question you should ask yourself. Is what we've designed too complicated? Can it be simplified? The second kind of leading on from this is, well, once we know exactly what our system needs to do, then can we simplify that? Do we can we simplify it? And then finally, if we've already got systems in place, is there anything that we can use about the previously created systems that basically avoid us doing extra work or like duplicating? I'm going to give a couple of examples of these things. And then the final thing, which is similar, is if we've already calculated some result, can we reuse that result again? And I'll also give you a couple of ideas for ways you might be able to do this. So again, going on to the pathfinding example here, if we need a pathfinding system, we don't necessarily need it to be the shortest path. A lot of what GameMaker offers as far as default pathfinding algorithms, using NP grid if you've used that, and this can kind of apply to lots of different things. It will give you the absolute shortest path between a source and a destination. And this, you don't necessarily need this for your game. Like you kind of have to consider how the game works and whether just any path would be valid. So we only want to find a path to a destination rather than the shortest path. And if you only need a path, then you can really simplify the process. So this is an example of a pathfinding algorithm I wrote, which basically just scans out. But the really important thing is that it only visits each block once. Algorithms like A*, which is used in the NP grid implementation, will basically update. It will expand out, but it will also update nodes as it finds a faster path. In this case, we don't really care about that. We just want to find, is there a path to a given cell in our grid? And if there is, then we get the path. Another benefit of this is we actually, the way this algorithm works, we get loads of paths for free. So once we know where the character is and we sort of spread out the grid, we can kind of get paths to any other cell on the grid. And if the player doesn't move and we just want to test multiple different locations, this is really good for AI. We can run this algorithm once and then instantly look up to see whether a certain location is accessible. This is something that's really useful in Pathfinders, whether you want to see whether an enemy can get from one location to another. But again, the algorithm ends up being really fast because it only needs to evaluate each cell once rather than revisiting. And when you start to kind of think about how these algorithms work, and especially the ones that are kind of behind the scenes in GameMaker, you don't really know what they're doing. You can actually start to come up with some better solutions that are more appropriate for your use case, rather than kind of generalizing it and having a more complex solution. This is kind of a more graphicsy one. And so a lot of times you have these sort of ray tracing problems in 3D graphics. And I appreciate a lot of you probably don't work in 3D. But this line of thinking can also be applied to a 2D game where you need to pick things up as well. And basically, it's quite like we can reason about wanting to pick things up in a scene and say, well, we want it to line up with what the player sees, right? So if you're playing a game and you need to pick something up and you're hovering the mouse over it, it's kind of intuitive that the thing that you want to pick up is the same object that the player sees and has their mouse over visually. A lot of people, when they want to think about how you'd pick up an object, whether it be in a 2D game or a 3D, will consider some form of ray tracing. In 2D, this may mean when you click the mouse, looping through every single object on the screen and checking if the mouse is above it, and then doing some weird kind of depth calculation to see if the object that you've clicked on is actually above some other object that was also clicked on. And it starts getting really ugly, really slow. And if you kind of rely on that for lots of interactions, it can slow down the performance a lot. So one technique you can use here, and given that you're already rendering your scene, this ends up, you basically get this for almost free, is a thing called an index buffer. And what an index buffer does is when you render something on screen, we can render a copy of that object to a separate surface, and rather than just rendering it as we see it, we can replace its color using a shader with the ID of the object. And then we can just use a simple pixel lookup to fetch information, to work out what object is below our mouse. And so once we've rendered our scene once, then we can work out where any object is in our scene instantly without having to do any extra work. The next thing is about load balancing. And this is to do with identifying scenarios where you don't need your results instantly. So again, for pathfinding, I'm mentioning this a lot because I know a lot of people have trouble when it comes to coming up with efficient pathfinding when they want to use it a lot in their games, particularly in games like RTSs where you've got quite a complex calculation to work out how you move a group of like characters who are grouped together from one location to another. It can be quite difficult to do that efficiently. And one strategy here is that you don't necessarily need to do it in one frame instantly because that could cause a stutter in your game. Like if you know that something is going to take more than a frame's worth of time to compute and you know it's going to create a stutter, then what you can do is basically distribute that over a series of frames and create an infrastructure which allows management of that. So yeah, so we might want to do that, and I'll give an example in a minute. The other thing we can do is caching. And the idea of caching is that we're basically trading memory usage to improve performance. And caching can be used for everything from just storing results we've already calculated in some data structure somewhere, or it can be used to sort of pre-compute data, load that in, and then that data exists there ready for us to use. So for an example might be if you've got like a level and you've got a certain way collisions are mapped out and there's a bit of processing that you need to do to work out where those collisions lie, you could pre-process that data, store it in a file, and then load that in some data structure, and it's ready to go. It takes some more memory, but it can speed up the actual practical use of it quite significantly. So to solve the asynchronous problem that I mentioned before, where you want to create some system that enables you to ask for some result, but not necessarily calculate it instantly, is we need a sort of task queue. And so in pathfinding, an enemy might be like, okay, I want a path from A to B, and what it'll do is submit like a function to submit some request to the pathfinding component of your project, and then over a series of frames, that component will tick away, calculating things, and once it has found a path or failed, a variable will get changed, and then that object can query whether its path is ready. And oftentimes you can do this to really give yourself control over how much time a particular algorithm is taking. So if you've got something that sometimes is really quick, but sometimes takes 10 seconds, this can be detrimental for the user experience because some player could walk in some weird area and suddenly you've got something that is unfeasible to compute in time, but because GameMaker is single-threaded, you end up in this scenario where your game just freezes for 10 seconds and there's nothing you can do about it. If you design your algorithms in a way where they kind of limit the amount of computation they can do over each frame, then you have much more control and can make guarantees about how long or how much processing time is going to be spent doing that task per frame. And this enables you to keep your game running at a smooth frame rate, which can be really important on devices, especially ones with variable performance, or if you've got variable scenes, you sometimes need a bit of control in certain areas to know, okay, we're only going to do at most like 2 path calculations per frame, because otherwise things are going to get too slow. So that's kind of a rough diagram of how you could design a system like that. So you've got entities that communicate with this request queue, and then the pathfinding system that makes progress on those paths. So caching, I'll skim through this because it's quite self-explanatory. Again, I kind of explained it earlier with the paths. Using this algorithm, it gives us loads of paths at once, and we can store all these previous paths just by maintaining the state of the grid. And then if any path that we want from this given location, we get for free. And the idea there is we're just storing previously calculated results. In practice, this may mean that each entity retains a grid like this for all the paths that are currently relevant for it. But there are lots of different ways of doing that. So this is kind of an example of a generic cache for a function that's quite computationally expensive. So for example, the factorial function is sort of progressive multiplication of numbers. So this is really expensive to calculate if you keep on needing it. If you need factorial, say if you've got like a level generator and you rely on something like factorial or something like Perlin noise, which involves performing a repeated calculation multiple times, it can be useful to store the results of that so the next time you use it, it's a lot faster. And basically all you do here is create a map, and every time you calculate a new result, just store it in the map. If it's already in the map, you just return what's already there. Really simple, and but can help you speed up slow functions a lot. The next thing I want to talk about is a brief overview on distributed programming. And the idea behind this is that we've got computers that have got 8 cores these days, and GameMaker can only use one of them. There are multiple ways that you can achieve distributed programming, and there are multiple sort of different applications of this. The most relevant is just to speed up your games, but it's also to improve the user experience, especially if you've got things, again, that can require a long time to compute. Say, for example, level generation that could take seconds. You can offload that somewhere and have that ticking away in the background, but also not even affecting the performance of your game in any way. So this is slightly different to the asynchronous thing where we're still running on the same thread. This is trying to get the most out of our systems, or even in a multiplayer game where you're considering managing server load. So for example, a lot of games, a lot of MMOs, which have got thousands and thousands of players, there won't just be one server that's processing all of those players. They'll have several different servers, and each server is responsible for different things. You've got one server maybe processing different regions of the map or processing different players. And the idea here is you can just use networking to basically spread out your processing. And again, this probably isn't relevant for most games, and it starts getting more advanced. But if you're trying to build like a big game which has got high demands, then it can become relevant. And sort of designing infrastructures, especially in co-op games, where you can offload different percentages of the work to all the clients rather than having the server or the main player just doing all of the work, can really help improve performance, especially when you're really trying to grasp for it, and also expand the range of computers that your game can be played on. Final thing is that multi-threading is something that you can achieve in GameMaker, and this can be done through the use of DLLs or through C++ code injection. I'm not going to talk much about this because it's not that relevant, but if you're interested, you can talk to me after or just message me online, and I'd be happy to explain how it all works. The idea here is that rather than having to worry about networking, we can have code running from GameMaker in the same application, but distributed across multiple threads so that we can get the most out of a system, and so that your 4-core computer isn't just running on one thread. And so, yeah, I kind of put a caveat down here. The main focus of this should be for improving the user experience, not necessarily for just making your game run faster, because at some point, if you're kind of targeting the PC platform, performance is so variable anyway that you cannot necessarily rely on having other free cores. But the main benefit of having cores is to smooth out things like loading screens so that they don't interfere, so that the user can continue to interact with the game while things are loading or saving or any operation like that. So yeah, this is kind of all what I've talked about. The final thing, this is probably weird that I'm mentioning this last, but local code optimization is probably the very, very last thing you should consider when optimizing. And this refers to things like if you've got some bit of code that's repeated twice. So for example, you're doing A plus B, and then later on in your code, you're doing A plus B again. This is kind of stuff that mostly gets optimized away by the compiler anyway. And it also can decrease the readability of your code if you start tweaking things excessively. So this might mean reducing an algorithm down and condensing it to the point where it's not readable, but you're doing kind of less operations per step. And a lot of people kind of start their optimization here. They'll look at a script and be like, oh, this script's got 100 lines of code. How can we trim that down so that we've got less operations? And they'll trim their script down to 20 lines of code or something. And suddenly, maybe they've sped it up by about 5 to 10%, but you can't actually read what the algorithm does. So the example here would be if you've got this bit of code and you're looping over, every time you run this loop, this condition, whether I is smaller than the size of the list, is checked. What we've got here is an actual function that returns the size of a list. And assuming that the list, like in this example, isn't changing size, we don't necessarily need to calculate and fetch this size every single iteration of the loop. We can hoist this out and just run it once and replace this with a size variable. And as far as processing goes, for an algorithm like this, which is really simple, that could probably double or triple the performance of that whole bit of code. But at the same time, it's one of these changes that in a bigger script where you're doing a lot of work inside that body wouldn't actually have much impact. And this code is actually very good for readability because you can instantly see, well, actually, the list. This is definitely the size of a list, not something else. So yeah, you should only do these once you've kind of finished your game in the final polishing stages. And the final thing I want to talk about is just when you should optimize your game in general, and why it might be relevant to you as well. So the final thing here is a quote, and you might have heard this, where people say premature optimization is the root of all evil. And that's basically what I've just described, where if your optimizations are resulting in your code being less readable, less maintainable, then it's not a good time to do it, because you might have a bug, you might have a problem down the line, and then suddenly your code's hard to read. So kind of, yeah, you should just save most optimization for the end of your project. The times it becomes relevant is if your project is clearly going to run into problems. So you've made 10% of your game and you're already suffering performance issues from the number of enemies who are on screen, but you want to have 10 times more. It's going to be obvious at that point that if your game is already lagging, it's going to lag even worse when you add more enemies. And that's when you should probably consider changing how you're doing things. And normally this will involve reconsidering the algorithms you're using, reconsidering the data path and how the CPU and the GPU are communicating to make sure you're just not wasting performance in the GPU. And then finally, everyone should optimize their games, even if it's a really simple phone game, because the last thing you want is for your simple phone game to be consuming all of your phone's like processing resources, draining the battery down so that you can only play the game for 20 minutes, and also overheating phones, which is quite a big problem for a lot of phone gamers. And you kind of think it's easy to think, oh, this game's really simple. It should run on anything, but some people try and play your game on this. So always be aware, even if you put in your minimum spec, okay, yeah, we need a graphics card, someone will buy your game, someone will try and run it on the 10-year-old Windows XP laptop, and then they'll still complain when it doesn't run. And even if you tell them, well, I'll put the minimum spec, it's best to try and have it be as good as possible, or at least potentially be able to run somewhat playably on an old system. So yeah, okay. So yeah, that's kind of everything. If you've got any questions, feel free to ask, and thank you for listening.